we feel pretty good about our model. We have an estimate of the slope, and we have an estimate for the intercept. And so we have a model that looks something like this. For any given value, we could predict what y is based upon our estimate of the intercept plus our estimate of the slope. And then there's our predictor variable, that xi. So for any given amount of nitrogen, we should be able to predict what the height of the plant should be. And of course, with all this is also the leftover stuff. But for our purposes right now, we can just ignore that leftover stuff. And so we have this. And so let's first think about what our statistical hypothesis is. And if we wanted to basically do a statistical hypothesis test for our model, what we're really interested in is whether or not this slope is different from 0. Because if the slope is 0, then all we're left with is the intercept, right? Because that would be 0 times something, which would mean that that doesn't matter at all. And then we would just be left with an intercept. And at that point, the intercept would simply be the mean of y. So it's just like when you're sampling from a normal distribution, your expected value, every time you sample from that population, the expected value is the mean, right? That is what the most likely value is. And then, of course, the variance tells you something about the spread around that. But the expected value is the mean. So if the slope is actually 0, that means that the best you can do is estimate the mean. But if the slope is different from 0, and you feel confident that it's different from 0, that means that your value of y will change as a function of x. And that's what our linear model is doing, is we're asking whether or not the amount of nitrogen in any way influences what our predicted value is for the height, for our y. And so our formal statistical hypothesis, again, our biological hypothesis would be something like, nitrogen affects the height of plants, or nitrogen doesn't, whatever, however you want to phrase it. Our statistical hypothesis, the null hypothesis, is going to be that the true beta 1 is equal to 0. And again, B1, that's our estimate of the true unknowable parameter, right? The population parameter. So our null hypothesis is going to be that there's no slope. So in our case here, nitrogen has no influence whatsoever on growth. Our alternative hypothesis is simply that our slope is not equal to 0. And so again, if we pop in 0 or not 0 into our linear model, the other way of phrasing these exact same hypotheses is simply going to be either the slope is equal to 0, or we could say that our best model, actually let's make that a beta. Let's keep it all consistent since we're dealing with parameters. So that's our null hypothesis. The best we can do is estimate an intercept. If the slope is equal to 0, that means that the intercept is the mean. That's the best we can do. The alternative hypothesis is that our better model includes not only the intercept, but includes the slope. Okay. And so that's the hypotheses that we want to test. Let's do that. So how are we going to do that? How we're going to do that is we are going to construct what is known as an ANOVA table. And I think I've already mentioned it before, and I will undoubtedly mention it again. ANOVA means analysis of variance. Analysis of variance is a way in which we can test hypotheses about a linear model. So we will use an ANOVA with a simple regression. We will use an ANOVA with a complex ANCOVA with factorial terms or whatever. Analysis of variance is simply the tool we're using to test hypotheses about a linear model. So let's think about that. So the first thing that we're going to need to do is we're going to need to construct what is called an ANOVA table. And we've already talked about how we've calculated the sums of squares, right? So the model sums the squares were the squared deviations of our predicted values against the mean of the response variable. Our error sums of squares were the square of the deviations between our observed values and the observed values and our predicted values. And then we had the total sums of squares, which was the deviations of our observed values from the mean. And so that is just simply the numerator of the calculation of variance. And in our case here, it was 16.1, what was it, 19, right? And yes, there's rounding problems here, but in principle, that plus that should equal that. Yeah, I clearly have some rounding issues there, but it's close enough for rock and roll, so we're good. So the next thing that we need to think about are the degrees of freedom, or the level of independent observations that we have at any of these given levels in the ANOVA table. So let's think about the degrees of freedom. The degrees of freedom for our model is simply the number of parameters we've estimated minus 1. And so in our model, down here is our full model. That is our full model. I can't move my computer because I'm having technical difficulties. It blows up on me. And so we've estimated 2 parameters in the model. We've estimated an intercept and we've estimated a slope. So that's 2. The number of degrees of freedom will be the number of parameters minus 1, which will be 1. So we have 1 degree of freedom associated with the model. For our error term, the degrees of freedom that we will have are going to be the total number of observations that we have, which in this case was 10. And we subtract from that the number of parameters that we've estimated. So again, remembering back to the whole Bessel's correction with the variance, where it was n minus 1 in the denominator, that was because when we were estimating the variance, we had already estimated 1 parameter. We had already estimated the mean. So we have n minus 1, so we don't have a biased estimator. Well, in this case, we've estimated 2 parameters. We've estimated the intercept and the slope. And so it's going to be 10 minus 2, which is going to be 8. And then for the total degrees of freedom, there's 2 different ways that we can calculate that. Much like there were 2 different ways that we could do the total sums of squares. We could either add these 2 things together, or we could just take the numerator part of the variance to calculate that. For the total degrees of freedom, we can either add these 2 things together, 8 plus 1, 9, or we could simply say the total number of observations minus 1, which is 10 minus 1 equals 9. So there you have it. 8 plus 1 equals 10 minus 1. We're good to go. That's arithmetic. Okay. So now we have our degrees of freedom for each of these. And then the next thing that we can calculate is what's called the mean squared. Okay. And the mean squared for each of these different levels is simply the sums of squares divided by the degrees of freedom associated with that level. And so in this case here, the mean squared for the model is going to be 7.47 divided by 1, which is going to equal 7.47. I'm good with that. The next thing is going to be the error term. The error term is going to be what? It is going to be 8.57 divided by 8. And I'm not going to do that one in my head. And I didn't cheat and do that beforehand. So I'm going to sneak over here and I'm going to do that really quickly. 8.57 divided by 8. 1.07. 1.07. And so that's our error mean squared. And then in an ANOVA table, get that into that picture, get that glare away from there. In an ANOVA table, the total mean squared doesn't really serve any purpose, so nobody reports it and nobody calculates it. But let's think about if we wanted to go a little rogue, you know, sometimes it's good to be a little bit of a rebel and say, hey, I'm going to calculate the total mean squared because the man told me I shouldn't. 16.19 divided by n. Well, let's think about where did that 16.19 come from? That was the sum of what? It was the sum of all of our observations minus the mean squared. That is our sums of squares, right? And then we're dividing it by 9. Where did we get that 9 from? That was n minus 1. That's variance, which means that the total mean squared is the variance. That's a neat thing to think about, because even though we don't calculate that, and again, we could. I mean, I'll just cheat and I'll just do it. I'll say, what is the variance of, what are we predicting again? Height. That's 1.78, okay? But again, this is never reported because it's not going to play any role in our hypothesis testing when we do the analysis of variance. But why it's kind of helpful to think about the fact that the total mean squared is the variance, because now we can step back and we can, at least as a thought model, we can start thinking about these as variance components. This is the variance component of our model. This is the variance component of the leftover variation that our model failed to explain. And then again, the total mean squared is just the variance. One thing to make an important mental note of is that you'll notice that now that we've gone to mean squares, these are no longer additive. And they won't be additive. Okay? But let's think about them as variance components, because that will end up being really handy when we start thinking about doing the hypothesis testing, that when we have these mean squares, what we have are variance components. So, okay. So now let's think about how are we going to test these hypotheses down here. The slope is equal to 0 or the slope is different from 0. And there's actually two different ways that we can test these hypotheses, especially with a model as simple as the model that we're playing with right now, where it's just a simple regression model where we have a single predictor and a single response variable, and we're just trying to understand, whether or not that slope should be in there, whether or not we're learning anything new and our predictive ability is increasing at all just by having some information about the nitrogen that was available. And so there's two different approaches we can take. The first approach that we can take, I'm going to erase all of our hard work. Kills me. There's so much hard work, and now I've ruined it. What we can do to test the hypothesis about the slope, right? So again, our null hypothesis is that the slope is equal to 0. Our alternative hypothesis is that the slope is different from 0. Okay, that is our statistical hypothesis. So one way that we can test the hypothesis for this model, and this is the important bit, we want to know whether or not that slope should be there or not. Are we learning anything by including that slope parameter in there? We can test that hypothesis using our old friend that goes back to the Guinness Brewing Company, the t-distribution. And we can do that by calculating a t-statistic. And then just as all the other types of t-tests that we've done. Now remember, we've done t-tests where we've compared the means of groups, but we also used a t-test when we compared the correlation. Well, here's another location parameter. Let's go ahead and use a t-distribution. So what will we do to calculate that t-statistic? Well, we'll take our observed value of the slope. There's our estimate of it, B1. Subtract from that theta. Theta is our hypothesized value, which is equal to 0 in this case. But again, we could change theta. We could do it, we could test, like, is the slope different from 2? Or is it different from 12? Whatever it is. But it's a general way of testing hypotheses about the model. Since we're interested in knowing whether or not it's even worth us including that slope parameter, theta is going to equal 0. And then just as before, we have to have some estimate of the uncertainty around that slope estimate. And so we're going to need to calculate the standard error around our estimate of the slope. And we'll get to that in a second. But again, this is a t-test. There's our observed value for our location parameter, in this case, the slope. There's our hypothesized value, in this case, 0, and the uncertainty around our estimate of the slope. This is the exact same formula that we used when we used the t-test to compare means, when we used the t-test to compare or to test hypotheses about the correlation, and now we're doing the same thing with the slope. And so, without worrying about getting too deep into the weeds of the math underlying that, we estimate the standard error of the slope. That is going to equal the square root of the mean squared of our error term, which we've already calculated. And then in the denominator here, we are going to sum, oh geez, that doesn't look pretty. Thankfully, this is all in the handout that hopefully you're looking along with and not trying to, yeah, it is what it is. I'm doing my best. We are going to take the sum of all of our values of x minus the mean of x squared, okay? And so this is the part that it might be counterintuitive. It's like now we're thinking about the sums of squares of x deviations. But all we're going to do is we're going to take the square root of our mean squared of our error term divided by the sums of square deviations around x. And that is going to give us our estimate of the standard error around our estimate of the slope. And once we calculate that, we can pop that into here. And then we have our observed slope minus 0 divided by the standard error around that. That's going to give us our t statistic. And then from there, we can just look at the t distribution and do some statistical hypothesis testing. What is the probability that I would get a t statistic that extreme or more extreme if my null hypothesis were true, meaning that the slope is actually theta. And in this case, the slope actually being theta is 0. Now we can also do the same thing, if we wanted to, with the intercept. Now, very, very rarely, if ever, do you care if the intercept is different from 0. I'm only going to walk through it here because it is output that computer programs will give you. And if you don't understand where those numbers come from, it's really easy to make the mistake of saying, oh, it's significant because the intercept is different from 0. And again, we really don't care if the intercept is different from 0. But we could test that hypothesis if we wanted to. And why not? If we got the power to do something, we might as well do it. It's a crazy world we live in, so we might as well embrace things that we actually have control over. And so what would we do? Well, we would take our observed value of the intercept minus some theta, which usually is 0, but it could be anything we wanted to, divided by the standard error around our estimate of the intercept. And again, without getting into the weeds and worrying about the math, and when I say don't worry about the math, I don't mean that the math is trivial and that you shouldn't understand it. I'm just saying you don't need to commit it to memory, because I would never have you commit something to memory that I haven't bothered committing to memory. And I'm totally cheating right now by looking at the same handout I've given you all, because why in the heck would I remember this? But the standard error of the intercept is going to equal what? I'm going to get rid of this just because I'm going to get rid of all of that. I'm going to rewrite that later. I'm going to take the mean squared of the error, and I'm going to multiply that by 1 over n, so 1 over my sample size, plus the mean of x squared divided by my sums of squares of x. And we know what the sums of squares are because it's all of the observations minus the mean squared. You sum up all of those, the sums of squared of x. This will give us our standard error around the intercept. So again, going back to our t-distribution, just like we did with correlation and we did with t-test, because this is a t-test, but we will calculate our t-statistic again by taking our observed intercept minus theta, which is 0, divided by our standard error of the intercept. We will get a critical t-statistic. We can then take that t-statistic, look at the cumulative distribution function of a t-distribution with the appropriate degrees of freedom, and ask ourselves, is the intercept different from 0? And so let's go ahead and do that really quickly in R so that we know where certain numbers come from. Because again, the t-statistics are always there whenever you do an analysis of variance, and it's often easy to kind of lose sight as to what you're supposed to do with those. So let's run through those really quickly with our friend R, because R will tell us what we want to know, because R is good at that. So what do we have? We have our model, which I've done right here. Okay, right there. Oh, I'm gonna do this again because I feel cool when I do it. There's our model. Our model is a linear model where the height in centimeters is some function of the amount of nitrogen. Okay, so we have our model. Here's our parameter estimates. And now if I were to type summary, so I'm asking R to just summarize my model. Give me the love, R, give me the love. And there it is. Okay. And so here we have our output, and it's going to give us like what the residuals look like, and we can talk about the utility of these in a bit when we do some quality control. But here's our coefficients. Here's our estimate of the intercept, and here's our estimate of the slope. Here is the standard error, and in both in the R code that I've given everybody and in the notes that everybody has, we go through all of the maths and we kind of show where that standard error comes from. And then we calculate a t-statistic. And then we go ahead and we could look at the cumulative distribution function for a t-distribution and ask what's the probability that I would get that value or a more extreme value. And then here's the associated p-values. And so the intercept is different from 0. Very rarely is that interesting. You usually don't care about the intercept because the intercept is really only there to give an anchor to that line that the slope is describing. But the important bit here is that the slope is significant, okay? Meaning that our slope is significantly different from 0. And that is telling us a little something about the fact that we probably want to keep the slope in the model. So we know that if, and this is a big if, but, oh man, I deleted it. I didn't need to delete it. The slope is either equal to 0 or, killing me, or the slope is different from 0. That's what our t-test right here is telling us, that based upon an alpha of 0.05, we will reject the null and accept the alternative, which means that the best way that we can describe our value for y, our height, is including the intercept in there. Because if this is different from 0, that means that we have our intercept and we have a slope. And that's the best way, based upon the data on hand, that we can estimate our value for y. And in this case, it is the height. All right. So there's the first way to think about the hypothesis testing. But we can also then sit back and think a little bit about the fact that we've calculated the standard error of the slope, going back to how we thought about with a normal distribution. Remember that the standard error around the mean told us what the expected standard deviation is around the mean, so the uncertainty of our calculating mu. Our standard error around the slope is similarly going to tell us something about the uncertainty around our estimate of the slope. And so we're going to want our uncertainty around our predicted values then are going to end up being a function of the standard error around the slope. And as that standard error is larger, then our uncertainty around our predicted values is going to be larger. And if our standard error is small, it's going to be less uncertainty. And so we can think about the standard error for any given value of y. And this is another piece of arithmetic that you don't need to memorize at all. I just want you to understand what it does. Because again, I don't memorize this, but I just appreciate what it's doing. And so what is this little math here? This is from the notes that I've given all of you. And here what we're looking at is, this is our predicted value of y given a particular value of x is going to equal the square root of our mean squared of our error times 1 over n plus, and now you'll see it's the squared deviation of that given value of x from the mean divided by the sum of all of our values for x minus the mean of x squared. Okay? And again, you don't have to worry about the arithmetic. One thing I do want to point out is that the mean squared, the uncertainty around our value of y for any of our predicted values, just based upon this arithmetic here, hopefully what you can kind of squint and see is that the further away our x values are from the mean of x, the greater the uncertainty will be around our predicted values. And so a way to visualize this is, here's our model, right? We have nitrogen and we have height over here, right? There's height, that's me writing it sloppily because I would invariably screw up and put the I before E or whatever, or the E before I, or however it would go. I don't know. That's why I wrote it sloppy. You'll never know. And then I have the nitrogen here. This is our prediction, right? So everything on this line is a predicted value. But because you can see that the error, the uncertainty around that, is going to get larger and larger as we get away from the mean of x. So if the mean of x is here, we're going to expect our standard error to be smaller than if we go out here away from the mean. If that's the mean of n, we're going to end up with larger errors. And as we'll see in just a second, because we'll make a really pretty graph with R, is that it'll look something like this, where we're going to have greater uncertainty around our values. I'll make myself bigger now so you can see, because I've done a really good job, I think, with my artistic rendition here. Pretty happy with that. Well done, Jim. We're going to have greater uncertainty around our predicted value of y as we get further and further away from the mean of our predictor, our mean of x. In this case, it's nitrogen. So we're going to feel better about having pretty high confidence about what our expected value of height should be if we're at an average temperature or at an average amount of nitrogen compared to if we are far away from it. So I'm going to hit pause, I'm going to reset, I'm going to get things all figured out, and we'll really quickly run through this in our... All right, now we're going back to Jim's native habitat, which is R apparently. So let's make me small. Let's make me small. And this is just going through a little bit of the code that I've already given you. So again, we have our standard error of the slope, and that is this. Where is it? Where did I do that? I did that somewhere. Standard error of the slope is, oh my goodness, right there. That's it. That's the beautiful piece of arithmetic that we're playing with. I just coded that in R, so I have a standard error around that. Okay, and so again, if we were to do a summary of our mod, That's where that value comes from. That is the standard error. That's where that number came from. We already know where the estimate came from. That was the covariance of x and y divided by the variance of x. So we understand where the slope came from. Our t-value, we set a theta at 0 because our null hypothesis is that the slope is equal to 0, and our alternative hypothesis is that it's different from 0. And so that's just simply going to be our observed minus our hypothesized value divided by our standard error, which we just calculated. So right now we can calculate our t-statistic. That is our t-statistic, 2.63. Hey, look at that. That's what R gave us when we asked for the summary of our linear model. And then the final thing, of course, would be to calculate a p-value. So we can do good old frequentist hypothesis testing and rejection. And I've done that here, looking at the cumulative distribution of a t-distribution. I have my critical t-statistic. My degrees of freedom are going to be the error degrees of freedom, which is 8 degrees of freedom. Why do we have 8 degrees of freedom? Because we've estimated 2 parameters. We've estimated an intercept and a slope. Every time you estimate a parameter, you got to ding yourself a random variable, so you got to lose a degree of freedom. And then I'm going to say lower tail equals false because this is positive. It's a positive value. So I'm going to be looking at the right-hand side of 0 if we think about the t-distribution. And then I'm going to multiply it by 2 because it's a two-tailed test. So the null hypothesis is that it was equal to 0, and the alternative is that it was different from 0. So it's a two-tailed test. It could either be different from 0 in a positive way or a negative way. So we're going to multiply that probability by 2. And then that is the p-value that we get. And then if we go back up here, that is the exact same p-value that we get there. Okay, so that means that when we hit summary mod in R and it spits out these things at us, we now know where these numbers come from. There is no magic there. We understand how we've estimated the slope. We understand how we estimated the intercept. We have the arithmetic where we could calculate the standard error around those parameter estimates. Once we have that standard error, we can go ahead and we can calculate a t-statistic. Because again, a t-statistic is a t-statistic. It's the same way as when we did t-test, and also when we used the t-distribution to test hypotheses about the correlation. Here we're doing the same thing where we're doing it with the slope. So it's just observed minus hypothesized divided by the uncertainty around our observed. And that's going to give us our t-statistic. And then again, we understand where then that p-value came from. And in the notes that I've handed out, we can also do the exact same thing for the intercept and calculate that longhand. And again, doing it longhand isn't something that you probably should ever really feel compelled to do unless you're doing something not weird, but unconventional. Like you're specifically interested in is the slope different from 0.8? Because somebody published a paper saying that it should be equal to 0.8. Then you would actually probably have to do it by hand or find another R package that would do it for you. But the most important reason why I like to go through these things longhand is that there is no mystery. There is no mystery to where these numbers are coming from. There's no magic. We can do it on the back of an envelope if we wanted to. Back in my day, people used to apparently do a lot of computations on the back of the envelope because people always talked about a back of the envelope calculation. So I just wanted to take the mystery away from that. So for our purposes here, I'm not going to do the intercept, but the intercept, solving for the intercept is both in the notes as well as in the R script I gave you. Where I want to go from here is I want to think about the confidence interval around the slope. And so remember when we were playing with the normal distribution, the 95% confidence interval was that interval where we were 95% confident that the true mean falls based upon our sample. We can think about that the exact same way with the slope. So we have a point estimate for the slope, which is 0.9176, and we have an uncertainty around that, which means that we should be able to calculate then the 95% confidence interval for the slope. Because right now we have a point estimate, but what we'd like to know is what are the range of possible values that we're 95% confident that the true unknowable slope is. And we do that the same way that we do the 95% confidence interval. So I will just cut and paste this from the code that I've given y'all. Here we have our estimate of the slope. And then what are we going to do? We're going to add to that the quantile for the 0.975 quantile at 8 degrees of freedom for the t distribution times our standard error around the slope. And so this is the exact same way that we calculated the 95% confidence interval around the mean, except here we're doing the 95% confidence interval around the slope. And so I can do that for the upper bound and for the lower bound. And then again, we have our observed, right? So here's our observed slope. And we are 95% confident that the true slope falls somewhere between 0.115 and 1.719. That's our 95% confidence interval around the slope. Now, there's a shortcut to do that exact same thing using a function called confint. Question mark, confint. Confidence intervals for model parameters. And what does it want? It wants the object. So it's going to want our model object, mod. It is going to want the parameter that we're interested in. Here, the parameter that we're interested in is nitrogen, parts per million. And then we're going to give it the level. And by default, it's going to say the 95% confidence interval. So I could go ahead and I could use that cool function, confint, which stands for confidence interval. We have what? We called that mod, right? Yes. Yes. So we have mod. Put mod in there. And then the parameter that we want to estimate is this, nitrogen parts per million. So I'm going to put that in quotes because that's what it wants, because it's a name of something. And then for level, I could just leave it blank because the default is 0.95, but for our purposes right now, let's be explicit and say I want the 95% confidence interval. I do that. There's the 95% confidence interval. Those are the same values that we got when we did it longhand. Again, this is what a rational human being would use to calculate the confidence interval around the slope. But to be an informed rational human being, let's take the mystery out of it and know where those values are coming from. And it's simply the same way that we did the 95% confidence interval for the mean. We're using a t distribution because it's a location parameter, and we're just multiplying that by the uncertainty, the standard error around that. And plus or minus that around the slope, that is giving us our 95% confidence interval. And again, we can do that just simply by using the confint function. So use the confint function, don't do it longhand, but just make sure that you understand where those numbers are coming from, because as I've said before, and I will say again, stats is actually super easy once you look behind the curtain or you open up the black box or you impose any other kind of metaphor that you might want to impose on it. And we could do the exact same thing for our confidence interval around the intercept. So we have our observed value of the intercept, and we have our standard error of the intercept. We can challenge that, or we can put that into the context of a t distribution. Oh, really? I didn't create that? Why didn't I create that? Sometimes I think I want to fail. Now I've created it. I must have. Intercept. Yes. And so there's our 95% confidence interval around the intercept. That's our point estimate of the intercept. Okay. And again, we could use that confint function, confint, for our mod. And then here, let's look at the name of the objects there. Notice that intercept is in parentheses. And so we're going to need to put it in parentheses when we put it into that confint function, because that's what the object is actually calling it. And by default, the level is going to be 0.95. But I will go ahead and be explicit with that and say 0.95. There's our 95% confidence intervals, which are the exact same numbers that we got when we did it longhand on the back of an envelope. Okay, So that's how we can think about those confidence intervals. And next, what we can do is we can think about what the shape of that plot might look like if we were to model that and think about the uncertainty. And so what I'm going to do, and this is only for graphical purposes, so if this is not helpful for you pedagogically, and I should probably mention this because in the past people are like, what the hell is that? Pedagogy refers to basically the underlying strategy or philosophy for teaching things to people. And so if this does not help you pedagogically, ignore it. But what am I going to do? So I'm going to center my data. I'm going to center the nitrogen data, and I'm going to center the height data. And I'm going to do that just for graphical plotting purposes. And so I'm going to go ahead and I'm going to do that like this. So I'm going to use the scale function, but I'm going to say scale equals false. So basically, here's all the nitrogen data, but that nitrogen data is centered around the mean. I have not divided it by the standard deviation because I said scale equals false. So all I've done is I've centered everything around the mean. And so like this first observation is 0.227 parts per million less than the mean of my entire sample. So I'm going to go ahead and I'm going to do that, and then I'm going to do this little as numeric thing just because R will be annoying otherwise. But here here's my heights centered around 0, and here's my nitrogen centered around 0. And so I'm going to go ahead and I'm going to make a new model based upon that centered data, and we can look at that. And notice that the slope has not changed, but the intercept is now at 0. Again, that's a rounding error in R. R doesn't know any better. It's doing the best it can as a computer. That is essentially 0 because we've centered all of our data. The intercept should go through the mean of X and the mean of Y. Okay? And so, and we could similarly take a look here at the confidence intervals around that. So here's our confidence intervals for the slope. That hasn't changed. The intercept has changed, but again, we're very rarely actually interested in that. And so let's go ahead, based upon those parameter estimates, and what I'm going to do is I'm going to plot them. So here's our data. And what I'm going to do is I am going to randomly draw from, based upon our parameter estimates of our point estimate and the standard error around that, I am going to randomly draw samples from that, and I'm going to think about all the possible slopes that we might deal with. And so, again, there's our observed regression line for our data. And now, given our estimate of the standard error, and we already know the 95% confidence interval of where things should fall, let's just kind of look at where those things might fall. And so I'm going to go ahead and I'm going to do that. Oh, come on, you're killing me. Escape. Okay. Now it's doing it. And so these are all the different slopes and intercepts that fit within our 95% confidence interval. Let me go back to that. Here it is. Okay. And I'm drawing them in there, and they're going in slowly, but you can see that as we get further and further away from the mean, this is the mean here, we have pretty tight interval here. And as we get further and further away from the mean, we have a larger and larger interval. Okay. And so that was that hourglass that I think that my artistic rendition is really nice, but this is the actual, that right there is the actual values. And so what we're doing is we're thinking about all the possible slopes, because the slope is a line, right? So it's going up and down because the intercept has variation and the slope itself has variation. So it's going up and down and back and forth and up and down and back and forth. And that's what we're looking at here. And so I'm going to go ahead and I'm going to pause that because it's thinking really hard with that. Escape. Okay. And what I'm going to do, yeah, so here's a bunch of them, right? That's probably 10,000 of them. You can see all those possible slopes and all those. And notice that some of them are wacky, right? Like, what the heck is that? but that's probably a value that fell outside of the 95% confidence interval. Because let's remember that we're at the heart of all of this, these are being modeled as normals. And because we use the t-distribution, they must be modeled as normals. And in principle, by chance alone, we could end up with something really wacky because, you know, the normal distribution goes from negative infinity to positive infinity. But the 95% interval is where we expect 95% of all of these different lines to fall. And we can plot what those look like. So the first thing I'm going to do is I'm going to create an object called predFrame, which is going to be a prediction data frame. And I'm going to look at the various values of nitrogen. And again, here I'm dealing with the centered data because it's just easier to visualize the centered data. It's easier for graphical purposes. But we haven't changed any of our data at all. We've just centered it by the mean. The slope is still the same. So I'm going to go ahead and do that. And so what I've done is I've created a data frame that goes all the way from -3 nitrogen, so way out here, to +3. And all I've done is I've made a sequence from -3 to +3, and I've come up with 50 different values. So now what I can do is I can use another function that's built into R called predict. And predict will give me what I want based upon my linear model. So I'm going to say I want to predict.c. And that's just because I should probably have said predict n, but yeah, this is really predicting the height. I'm going to say predict, and I'm going to predict what? It's going to be based upon my model, because again, we have a model, and our model we are really happy with. That is our model. So I'm going to predict based upon that model. The interval that I want is the confidence. Confidence. That is how you spell confidence. Good. And then I'm going to give it new data. So if I were to just run that, that's going to just give me my actual data, my fitted values and my uncertainty around my fitted values. If I want to give it a whole range of data, I could say new data equals, and it's going to be all of those possible values. Because at the end of the day, we've made a model. We'd like for our model to be predictive of something in nature. So now what I want to know is, what are the predicted values for height for 50 values from -3 to 3 for the amount of nitrogen? So now I have that. Okay, so here's the fitted value, and that's just plugging it into the linear model where y equals b plus mx, essentially, right? Y equals the intercept plus the slope times the value. And I'm doing that across from nitrogen ranging from -3 to 3. And then what the predict function is giving me is giving me the fitted value. So those would be the values on the line. And then it's going to give me my lower value and my upper value. And then I'm going to plot that on this plot so I can see what it looks like. And to do that, I can use a handy little function called Matlines. Matlines stands for matrix lines, meaning that you can give it a matrix-like object, and it's going to draw lines for all three of those things that are on there. And so I'm going to say matlines pred.frame, because that's the name of that object. That's going to be the x-axis. And then I'm going to give it all of those different predicted values. And there's three different values that are part of pred.c. Pred.c includes the fitted value, so the values that are on the line, and then the upper and the lower, right? Or the lower and the upper, I guess I got those backwards. And so because of that, I'm going to change the colors just so that way they look pretty when we look at them. So I'm going to say that the color is going to equal, I will say that my fitted values, I will say that they're black. And then for the 95% confidence intervals, I'm going to say that those will be red. And then just to make the graph look fancier and prettier, I'm going to say that my line widths are 3, so that way they're big. That way they're not little small, little measly lines. They're going to be big fat lines. And then I'm also going to say line type. And what I'm going to do is I'm going to change the line types. For the first line type, for the fitted value, I'm going to say line type 1, which simply means a solid line. So it's going to be a solid black line, which is going to overlap perfectly with this solid black line because that's the fitted values. But then for the confidence intervals, I'm going to say line type 2. Line type 2 is just going to be dotted lines. That's all I'm doing there. So if I go ahead and I do that, oh, where is it? Where is it? Jim, you're killing me. Hold on. Oh man, how anticlimactic is that? I was so excited about everything I was just about to do. And now it's all gone. Let's try this again. I'm going to go ahead. I'm going to do that. All right. So that's all of our possibilities that we have sampled from that. And then if I were to stop that, go back to this, and now use Matlines. Oh, it's right there. Good. Okay, so these dotted lines here, that's the 95% confidence interval around the slopes. The black line here is our fitted values. And you can see that some of these slopes and lines, they kind of go outside of that 95% confidence interval. But only 5% of them do that, hence 95% confidence interval. We are 95% confident that the true slope and the true line that describes our data falls between that. And so again, as you get further and further away from the mean of our predictor, you have wider and wider confidence intervals around that. Okay, and so let's go back to our original data, right? Our original model. And so somewhere in, I'm just going to make a new model. I'm going to call it, to make it easier for myself, I'm going to call it model. It's going to be a linear model where what? Where height is some function of what? Nitrogen parts per million. Yes. Okay, that's our linear model. Again, it's right. Oh, I gotta hit escape. There it is. There's our linear model, right? There's our intercept and there's our slope. And I will go ahead and, using the real data now, I'm going to create a prediction frame, a data frame that I'm using for predicted values, where the nitrogen parts per million, I'm going to go all the way from 0 to 20. And I'm going to come up with 50 values for that. So that's going to give me my predictions, right? That's going to be the values. I'm going to say, what do I think the height is if there is 0 nitrogen, if there is 0.4, so on and so forth. I'm using my linear model to predict something about the universe. And that's the whole point behind doing statistics, is to understand the observable universe as we know it. And so I can come up with then the confidence interval around that. So I'm going to predict the confidence interval. There's our model. Again, that's our model. I'm going to tell it that I want the confidence interval. And the new data is this new possible nitrogen values. I do that. And so I can plot our data. And then I can use the abline function, abline our model. That's going to give us our regression line. And now what I can do is I can say, well, what are our fitted values, right? So based upon our actual sample, I'm going to just make little red dots on the regression line of what the fitted values actually are. Okay, so again, we've already looked at some of these, right? This is the residual. This is what our expected value is. This is our observed value. That's the residual. These are our expected values. And now we can go ahead and we can use the Matlines function. Matlines. And what are we going to do? We're going to, on the x-axis, it's going to be, again, our pred frame, dot frame, which are these possible values of nitrogen from 0 to 20. and we're going to say I want to plot that on the x-axis. On the y-axis, I want my confidence intervals from using the predict function. And then I'll do the same fancy stuff that I did before, where I'm going to change the colors and the line types, just because it'll look fancier, and we want things to look fancy, darn it. And that is our 95% confidence interval around our regression, essentially, our line, our slope. Well, no, not slope. It's the slope and the intercept, because again, the regression line itself can vary. Oh, this is actually working. And so can the elevation. And so if you're pivoting and you're going up and down, you end up with this nice hourglass shape. And that is our 95% confidence interval around the our predicted values. And so just like when we were playing around with the normal distribution, we had the 95% confidence interval, which is our 95% confidence interval about the mean. We could also think about, where do we expect future samples to fall? Remember, because when we did future samples, we used the normal, and when we used the 95% confidence interval around the mean, we used the t-distribution. Well, we can use this same predict function to think about, where do we think future individuals in that population should fall. And we can do that by using that predict function. So I'm going to cut and paste right from our little notes here, where now I'm going to say that the interval is the prediction interval. And this is about where the data are going to fall. Okay? And so just like when we did the 95% confidence interval, which was about the mean, that was relatively small compared to where do we expect 95% of the samples themselves to fall. And so we can go ahead and we can do that, and I will go ahead and I will plot this. And so again, here's our data. That's our regression line from our linear model. That's our prediction interval of where we expect 95% of the samples to fall. And you can see that it's much wider, but it was the same thing that we saw when we were playing with, where do we expect 95% of our samples to fall, as opposed to where are we 95% confident that the true mean falls. And so if we zoom that plot out a little bit, now I'm zooming it way out, there's all of our data hidden there in the middle. And we can go ahead and say, well, there's our 95% confidence interval, okay? And then we can look at our prediction interval. And notice that our prediction interval is much greater than our confidence interval, which makes sense because the confidence interval is about our estimate of that point estimate of the slope, or the expected value, which is the same as the mean, except here in a regression, the mean is changing as a function of nitrogen. And then this outside bands here with the smaller dots, that's where we expect the actual data to fall. Okay? And so a lot of times people like to present the 95% confidence interval around their slope when they're showing their model results, because it's a way essentially of being intellectually honest and showing where the uncertainty actually falls. So one caveat with this, and this is an important thing to remember with any kind of models, is that first of all models are wrong, some models are useful. That's an important kind of glib thing to always remember. But it's very risky to extrapolate beyond the range of our data. So like looking at our data here, I feel probably pretty good about, what would I expect the height to be if you had 8 parts per million, right? Because that's kind of nested within all of our data here, and I feel kind of good about that. It's very dangerous to extrapolate beyond the range of your data, because the model might not be appropriate beyond the range of the data. So with this example here, where we're dealing with nitrogen in plants, a little bit of biology 101 will tell you that plants can't grow without nitrogen. So if you have 0 nitrogen, your plant ain't gonna be 10 centimeters tall. It's gonna be dead. but the model is predicting that it's 10 centimeters tall. Again, the model is doing a pretty good job explaining about 50% of the variation within the range that we've looked at, but you have to be incredibly cautious when you start extrapolating beyond the range of the data, because this will not be the height of a plant with zero nitrogen. The height of a plant with zero nitrogen will be zero because it'll be a dead plant. Likewise, as anybody knows who is a failed home gardener, if you dump too much nitrogen, you can also kill the plant. So it's unlikely that if you start putting, 20 parts per million, you don't know for sure that you're actually going to get a super tall plant, because at that point, the plant might start to get sick and start dying out. So beyond the range of our data, I don't trust our model, and neither should you. But that's not to say you shouldn't love your model, because we really have to love our model. We worked hard to make our model. You gotta love your model, people. I can't emphasize this enough. You gotta take it for a walk. It needs some, it needs, playtime. It needs everything. You have to love your model. But don't expect your model to do something that it wasn't built to do. And this model was not built to extrapolate beyond the range of our actual data. So be very cautious with that whenever you're playing with anything with models. Okay, so we've done hypothesis testing on our model using the T distribution as a way to test our statistical hypothesis. And we've also now figured out how we can calculate confidence intervals around our estimate of the slope. And we also can calculate where we expect 95% of the actual data to fall, future samples to fall if we were to go out and sample those. So we have a prediction interval, we have a confidence interval, we've done our hypothesis testing, but there's one additional way that we can test hypotheses using an ANOVA. And it's the way that everybody tests hypotheses on these linear models. And that is to actually do an analysis of variance. So we've already built up a lot of the parts of the ANOVA table, but there's one extra part that we have to think about if we're going to use that for statistical hypothesis testing. And drum roll, we get to learn 2 more distributions, and those will kind of be the last distributions that we cover, which is sad, but we get to learn 2 more distributions. So buckle up. We got some more distributions to think about. I'm gonna pause. All right, so we're back at our ANOVA table that we had played around with, and we know where the degrees of freedom are coming from for our model, our error, and our total. We've talked about where the sums of squares are coming from, and then we've also talked about the mean squared, and we've used the mean squared to calculate the standard error of both the slope and the intercept. And so we've started to build up what is the classic ANOVA table. And we've already tested the hypotheses about the slope, so we could be fine and just leave there. But that's generally not how people do hypothesis testing with an ANOVA. And so this is where the mystery comes in, right? And so what we're going to calculate is what's called an F statistic. And a little bit cart before the horse. Our F statistic is simply going to be the mean squared of our model divided by the mean squared of the error term. And that's going to give us what our F statistic is. And that's great because we can use that F statistic, and it's a distribution, so there's a built-in function, the probability cumulative distribution function for an F, and we can calculate a p-value. But let's think about what this F distribution is. And this is, as I promised, we are going to talk about 2 additional distributions, one of them being the F. But to understand what the F distribution is, we need to understand what the chi-squared distribution is. Because the F distribution, wait for it, is actually the ratio of the chi-squares divided by the appropriate degrees of freedom it's the ratio of two chi-squared distributions. So at this point, that means absolutely nothing to you, and I am dead to you, and I accept that. I get it. Yes, you're right. That makes no sense because probably in the past, if anyone here has ever played with chi-square distributions, you associate it with a particular type of test for like a contingency table. And the only reason why those are called chi-square tests is because they're modeling aspects of it they believe are chi-squared distributed. But what the heck is a chi-squared? That's an important thing. The chi-squared is the sampling distribution for the expected sums of squares when you're sampling from something. And so remember that when the numerator of when we calculate the variance, that's the sums of squares, right? And we had that whole series of numbers, and then we divided that whole series of numbers by n minus 1, and that gave us the variance. Well, that numerator part, that squared deviations from the mean, we can assume that those themselves are random variables drawn from a distribution. And that distribution that they're drawn from is the chi-squared distribution. That is what the chi-squared distribution is attempting to model. And so as a proof of concept, well, first let's look at a chi-squared distribution. Let's just look and see what it looks like. So if it's based upon the sums of squares, we know that it can't have a negative value because we're not dealing with imaginary numbers. Statistics is imaginary enough. We certainly do not need any to introduce imaginary numbers to that. And because it's squared, we know that it's positive. So for example, this, using that curve function, oh man, you're killing me. I'm gonna close this, close that. I'm gonna try to do that again so that our studio, there it goes, thank you. And so this is the sampling distribution of a chi-square distribution with 1 degree of freedom, meaning that you have 2 observations and you can calculate the mean, and then you could look at where each of those observations fall relative to the mean and you square it. The sampling distribution that those values are drawn from, that is what a chi-square distribution is. So that's a chi-square distribution with 1 degree of freedom. Here's one with 4 degrees of freedom. Here's one with 8 degrees of freedom. Okay, so the chi-square distribution will change its shape based upon the number of degrees of freedom. The number of degrees of freedom here are the number of random variables that you actually have. And so again, even when you're thinking about calculating the variance, that numerator part of the variance, we are going to assume that the numerator is chi-squared distributed. And so to show that this actually works, I'm going to do a proof of concept simulation. Again, you don't have to sweat the code. You'll never have to do this code, but I'll walk you through it to explain what the heck Jim is doing. I'm creating an object called QZ, which are going to simply be a vector that is going to be the sum of the squared deviations from the mean. Okay, so again, this right here, that right there, that is the numerator of variance. And what I'm going to do is I'm going to do it 10,000 times. I am going to sample 3 random variables from a standard normal distribution with a mean of 0 and a standard deviation of 1. I'm going to randomly select 3 of those, and I'm going to calculate the sum of squared deviations from the mean. So I'm going to go ahead and I'm going to do that. That was a lot of work. So now I have a vector that is 10,000 long that has all of those values from those. And then let's plot using a histogram what those look like. So here they are, okay? And so this again is the culmination of 10,000 draws from a normal distribution. 10,000 times I sampled 3 things and I calculated the sum of squares, the numerator of variance, okay? And this is what that distribution looks like. So now let's compare that against a chi-squared distribution. with 2 degrees of freedom, because I took 3 draws. Again, once I start estimating the sums of squared deviations from the mean, I've already calculated the mean, so I have to lose myself a random variable. And so if I'm right, and I am, because obviously I've made sure that I'm right because I'm looking at my notes here, but you should all be excited because, oh wow, this makes sense. Cool. The shape of the chi-square distribution with 2 degrees of freedom should look a heck of a lot like our empirical brute force simulated data. And I do that, and let's see if I can make that work without getting an error. There it is. So there's a chi-square distribution with 2 degrees of freedom. And if you look at the shape of that, that looks a heck of a lot like what we empirically got when we were drawing those random variables out. And we can even go further, and we could say, well, okay, I have this chi-squared distribution. What is the quantile? Q chi-squa. That is the function for a chi-square distribution. And I want the 50th percentile, and I have 2 degrees of freedom. Okay, that's the arguments that are, I'll be explicit, and I'll write degrees of freedom. Okay, so I want to know what is the value of a chi-squared at the 50th percentile with 2 degrees of freedom. I do that, and it's 1.386. Okay, I can go back to all of our simulated data, and I can ask empirically, what is the 50th percentile? So I'll use that quantile function. And when I use that quantile function, I'm going to give it my Q's that I made. Again, that's all this stuff over here. That's what I made with the simulation. And I want to know the 50th percentile. I should probably put a comma there, or else I'll get an error. Okay, I'll do that. And look at that. It's really stinking close, right? And hopefully that brute force example has convinced you that, okay, I now get what a chi-squared distribution is. A chi-squared distribution is simply modeling the numerator of our calculation of the variance. So now going back to our ANOVA table, what we're asking, let's get rid of this for a second. I'll rewrite it in a second because I like writing it. What we're asking when we're doing the hypothesis testing is we're asking, is it worth including the slope, right? I mean, that's what we did when we did the t-test on the slope. It's like, should it be 0 or should it be something different from 0? What I'm asking here is, do I think that by including the slope, and that's our model, is that explaining enough of the variation that I think I should keep it in the model? And so to do that, we'll calculate our F statistic. Our F statistic is the mean squared of our model divided by the mean squared of our error. And so what we're looking at here is just, essentially, it's just a ratio of how much is our model explaining versus how much is our model not explaining. That's going to give us our F statistic. Our F statistic, because think about what the mean square of the model is. The mean square of the model, that's just the sums of squares divided by the degrees of freedom, right? That is essentially the variance component. Remember that the total mean squared is the variance, but we don't use that here because we're only interested in what we know, what we don't know, not the total of what kind of variation there is. And so the F statistic, we calculate our F statistic as the mean squared of the model divided by the mean squared of the error. But the mean squared of the model, that's what the chi-square distribution is doing. So the F is simply the chi-squared of our model in this point divided by the appropriate degrees of freedom divided by the chi-squared of our error term, the second distribution, divided by its appropriate degrees of freedom. Well, that is the exact same thing as the mean squared of the model divided by the mean squared of our error term. And that's what the F distribution is. So let's take a look at what the F distribution looks like, because all the F distribution is just the ratio between two different chi-squares. And this is why we use the F distribution when we do an analysis of variance, because the F distribution, that's exactly what it was built for, is to think about the relative amount of variation explained by our model versus the unexplained variation. Yes. Okay. And so let's take a look at what the F distribution actually looks like. Let me make a new killing me par mfro 1 and 1. All right, now I'm gonna have one little thing. Okay, so there's our F distribution, and let's I will label it. And so the black line here is the F distribution with 1 degree of freedom in the numerator and 1 degree of freedom in the denominator. Okay, so for us it's 1 and 8. The F distribution always has 2 degrees of freedom associated with it. If you ever report an F statistic, which invariably you will at some point, you certainly will in this class, but in the real world, you might also present an F statistic. You always have to tell people what your numerator degrees of freedom were and what your denominator degrees of freedom were. And here, the numerator is the model, so there's 1 degree of freedom, and the denominator is the error term, 8 degrees of freedom. So you have 1, 8 degrees of freedom. You have 2 degrees of freedom associated with that. So if we just looked at that, that is the F distribution for 1 degree of freedom in the numerator and 1 degree of freedom in the denominator. That is the ratio between these two chi-squared distributions. And again, all the chi-squared distribution is it's the sampling distribution for the sums of squares. And so I included all of the other F distributions in there just so you could see the variety of shapes that the F distribution might take. And so once we have that calculated F distribution, so in our case here, what is it? We have the mean squared of our regression divided by the mean squared of our error. It is 6.96, okay? And so if we were to write this up, like if we were presenting this to people, I'll make myself bigger. I'm going to go to Holiday Inns across the country and make people feel better about themselves. Make yourself bigger. So our F, how we would present this is we would say our F with 1, 8 degrees of freedom equals 6.96. And I keep emphasizing this degree of freedom thing because a lot of people forget to include that. And without the degrees of freedom, this number is dead to me. It means nothing. This number means something once I know what the numerator and denominator degrees of freedom were. There's the numerator, there's the denominator, 1, 8, 6.96. And so now what we can do is we can look at the F distribution and we can say, what is the probability that I would get a value this big or bigger conditional on the null hypothesis being true? And if the null hypothesis is true, then we would expect the error to encompass all of our variation because we're not doing much here with the slope part of it, okay? And so we would expect basically the mean squared of the model and the mean squared of the error to be the same value, and we would get an F statistic of 1 or even less than 1 depending on how the variance is distributed. But this is the key value that we want to look at. And again, 1, 8, always show your degrees of freedom when you're playing with an F statistic. And so let's go ahead and do that. So we can use the cumulative distribution for an F, which is PF. And what do we get? We got 6.96 you'll see here that it's requiring 2 degrees of freedom, degree of freedom 1, degree of freedom 2. So that's the numerator and the denominator. So 1 comma 8. And we're going to say lower tail equals false because we care about a value that extreme or more extreme. So we do that, and there is our p-value. And so we would say that f is 1.8, or no, f degrees of freedom 1 and 8 is 6.96. P equals 0.29, 0.029, right? That would be our p-value. So we would reject the null hypothesis, and we would accept the alternative that we should keep with our model. We did good. We did real good. Our slope is good. Okay, and so that's how we do the analysis of variance, and we come up with the p-value associated with our analysis of variance. And so here's the neat thing. Let's go back and look at, we have our model, right? There's our model, and we're proud of our model. I love our model. I feel good about it. I'm going to take it for a walk when I get home. There's our model. And remember that when we did summary of our model, we got a p-value here based upon a t-test. Now if I do an ANOVA on our data, ANOVA is the function I can use, model. Notice that we get the exact same p-value as we got with the t-statistic. And even cooler, let me kill that. I'm going to make myself reappear. New movie recording. I disappeared. It froze. How long was I frozen for? Did I look like an idiot? I might have looked like an idiot. Oh. Whew, where was I? Oh, right. So if we look at that t-value that was associated with the slope, here's a cool thing. Really cool thing. I take that value, I square it, and look at that. That and that. They're the same value. There's rounding errors there, obviously. But they're the same value. So, really cool thing. This is the thing that just like, you'll get so excited you won't be able to sleep tonight. You won't be able to sleep. You're going to be so excited by this. T squared equals F equals chi squared divided by chi squared. All three of those, oh, that light, these lights. I'm shadowing it. Oh man, killing me, just killing me. There, I'll pull it up next to me. T squared equals F equals the ratio of 2 chi-squares divided by the appropriate degrees of freedom. All of these distributions all revolve around our old friend, the standard normal. That's my artistic rendition of a standard normal distribution. They're all related to it. They're just telling different parts of it. The t squared, or the t distribution, is all about your estimate of the mean, your location. The chi-squared is all about that spread parameter, right? It's the sums of squares. The ratio of 2 of those is the same as f. So all 3 of these distributions are super tightly linked to one another, and they're all telling the same story, just from a different perspective. And it's a story about your modeling of something that is based upon a normal distribution. And so when you're playing around with using ANOVAs, there's a reason why that t-test gives you the exact same p-value. And it does give you the exact same p-value. There's our ANOVA, 0.2977. There's our p-value from the t-test. They give you the exact same answer because they're just different flavors of the exact same thing. So play around with that and think about that. We're going to be using the F distribution a lot for the next 4 or 5 weeks. The F is the standard way in which people do hypothesis testing with an ANOVA. And we use, again, the F distribution because we're comparing variance components as opposed to kind of focusing in on the location parameter. But both of these are very valid ways to test the hypothesis for our particular purposes with this particular model with a single predictor. And so, yeah, that was pretty cool, I think. I think it's pretty cool. And so just some final things to kind of think about. Well, almost final things. We got one other thing that is kind of a bigger deal that we need to think about. But let's say that we did a reduced model. So I'm going to create an object called model.r because it'll be a reduced model. And let's say that it was a linear model where I'm trying to predict height in centimeters. But then if I just did that little squiggly and I put 1 there, what that's telling R to do is don't estimate a slope, only estimate the intercept. And so if I were to do that, that is the intercept. Because the slope is not in there, the intercept then is the exact same thing as the mean. So if I were to say, what is the mean of height in centimeters? It's the exact same value. And so when we're doing this analysis of variance, what we're asking is it worth me estimating a slope, meaning that that expected value should change as a consequence of my predictor? Here the predictor is nitrogen. Or is the best I can do is to just simply say, here's the mean and the standard deviation of height, and I don't know how to predict any better than that, okay? And so we could compare those two models. Let's go ahead and I'll just retype it. The other alternative is we have a model, which is a linear model, where height is some function of nitrogen in parts per million. So now we have two competing models. We have one model where all we do is estimate the mean, because that's all we can do, and then we're going to compare that against a model where we have two parameters. We have a slope and an intercept. Another way that we could do that same hypothesis testing is using that ANOVA function. And we could just simply say, I want to compare my reduced model with my full model. And look at that. We get the exact same p-value. Degrees of freedom, we have 9 degrees of freedom if all we do is estimate the intercept, which means that all we've done is estimate the mean. And then we have a second model where we have 8 degrees of freedom because we've lost 2 because we've estimated both an intercept and a slope. And we can compare those two models and we get the exact same p-value once again. And that's the beauty of it, right? And it's like, where does this come from? Well, we could take 16.0450 minus the amount of variation that's explained in the for the full model, and divide that by our residual mean squared, which was 1.0723, which is the same value that we got way up here when we did the ANOVA function. So we do that, and look at that. That's where we get our F statistic. So yeah, so that's another way that we can compare those two models, okay? And again, we could take, just to drill this into our heads, we got the summary of the model, which will give us the T statistic approach. We can take the ANOVA approach for our model, which will give us the exact same answer, saying that nitrogen is significant, meaning that we should include a parameter that describes how the expected value in height changes as a function of the amount of nitrogen that we have in there. And again, T squared equals F equals the ratio of those two chi-squares. And so they're all related to one another. And yeah, that's analysis of variance. And the cool key thing is hopefully we know where all those numbers came from. There's no magic there. It's just partitioning the variance. And up here with the summary, We know exactly where all those numbers come from because all we're doing here is we're doing hypothesis testing on the parameter estimates using the t-distribution. And now we understand why we get the exact same p-value is because they're just different flavors of the same thing. We're trying to understand the variation and the uncertainty of our parameter estimates relative to a normal distribution. So on that, I'm going to hit pause, and then we're really briefly going to revisit our old friend power, because it's really important that we always remember how to do power. All right, power. We already know what power is. We've talked about power a lot. And what we can do is we can do a power analysis on our regression. And so here we had a significant slope. So maybe we don't really care that much about power because, hey, we rejected the null. I don't, maybe you're just fine with that. But it's always a good idea, especially if you fail to reject the null, to understand how to do power. And it's always good to remind yourself that it's worth doing a power analysis. So starting back up with our summary of our model, right? There's our information, all of that. And we have here our r squared. And we already talked about how we calculated the r squared. The r squared was simply the sums of squares of our model divided by the total sums of squares. And so we have our r squared. And so what are we going to do with that r squared? Well, that is how we're going to come up with the effect size. So remember when we were dealing with like comparing means, we had either the raw effect size or the standardized effect size, which was the number of standard deviations different. And then when we did a power analysis with the correlation, our effect size was the Pearson product moment correlation coefficient. So here to calculate the effect size, which I will call F2 because that's going to be the argument that we're going to put into the function, is simply going to be our r squared, 5654, yeah, nope, that's right, 4654, divided by 1 minus 0.4654. That is how we calculate the effect size for a simple linear regression, or really any linear model, but in this case, since we're dealing with a simple linear regression, we'll keep that language there. And then what we can do to test for power is load up that package called PWR. Ignore the warning message, because I love ignoring warning messages. And then the function that we'll use is pwr.f2.test. And if we look at what that wants, pwr.f2.test, it's going to want the numerator degrees of freedom, it's going to want the denominator degrees of freedom, and it's going to want our effect size. So our numerator degrees of freedom, again, was the degrees of freedom associated with the model. That's 1 degree of freedom. Our degrees of freedom associated with the denominator, that is our error degrees of freedom. That was 8. And we now have what it's asking for here is F2, which is the effect size, which is why I called that object F2 for ease. And so we'll go ahead and we'll just say that F2 equals F2. And I guess we could, if we wanted to, we could be very explicit. U equals that, V equals that. And we'll leave everything else standard because we're trying to solve for power here. So the significance level we'll keep at 0.05. So we go ahead and we do that. And that is the power that we have. So based upon that sample, that means that we would expect to miss that importance of nitrogen 27% of the time based upon our sample. And obviously if we increase sample size, that will increase our denominator degrees of freedom, and we will have more and more power. And so that's how you do a power analysis for a simple linear model. In this case, it's a simple linear regression. Okay, that's all.